will come back at some point. Okay, so then how do we solve this problem? So this is what we call the pre-flashover compartment fire framework. And it's an approach that was developed in the 1970s and effectively gives us a very coarse, but to some extent effective solution to the problem. And obviously, if you think of the 1970s, the emphasis was in minimizing the computational cost. I mean, the capacity of the computers that they had was minimal, and therefore they had to create frameworks that required a much, much lower computational cost. So if you look at the problem, the first thing that we have to do is identify what are the features that will carry the biggest computational cost. So if you think of this particular problem, what do you think will be key aspects of this problem that will require a very significant computational cost?
Generation and mixing of the fuel from the air.
Mm-hmm. Okay. So basically, all the phenomena that happens here, which effectively is Navier-Stokes, because you're going to have a three-dimensional flow that is feeding this. So it's three-dimensional Navier-Stokes. You're going to have complex chemical kinetics that result in generation of heat. Then you're going to have heat transfer to the surface that produces the fuel that eventually is going to burn. And then you're going to have radiative exchange between the flames and its surroundings. Okay? So that in itself is a huge computational cost. Now, obviously, the fluid mechanics eventually have to encompass the entire compartment because the entire compartment is going to create a flow. So the flow is going to come in through the boundary, enter the compartment, combust in here, go up, and then come down and then go out. This is basically ambient pressure system where effectively pressure is fully translated into fluid mechanics, so it behaves as compressible flow. Okay, it's only incompressible in the buoyant term. In other words, Boussinesq approximation applies, but in essence, is a solution to the three-dimensional Navier-Stokes equations, coupled with the heat exchanges happening at the flame level and potentially happening at the smoke layer. So radiation carries significant computational cost, and therefore radiation also needs to be addressed. So how do they simplify the problem? So effectively, the first approach is we take the smoke layer and we actually treat it as an adiabatic control volume. In other words, we assume that all the energy that goes into the smoke layer, TU, is going to remain within the smoke layer. We can make simple corrections to try to extract some heat, for example, for cooling against the ceiling or for radiative losses, but in essence, a conservative assumption will be to assume that all the energy remains in the smoke layer. In other words, this is an adiabatic control volume. Okay? That prevents me from having to solve the radiative equations for the smoke layer, and it is conservative in nature because the temperature is going to be higher than reality. Okay? So it's an error, but it's an error that goes on the conservative side. Now, how do I solve the problem of the Navier-Stokes equations and the fluid mechanics? Effectively, I treat this as two control volumes, the cold control volume and the hot control volume. And the only exchange that exists between those two control volumes is mass transfer. So in essence, what I'm going to be doing is transferring a certain amount of mass from one control volume to the other control volume, okay? And basically ignore the fluid mechanics because the fluid mechanics themselves in a stratified system will have a very, very limited impact in terms of the compartment itself. Okay? Think about it. What you have is a system that is stratified. So all the momentum is going to basically be absorbed in the interior of this, basically mixing the smoke in a way that you can assume that the entire control volume is at an homogeneous temperature. So there's no longer X, Y, and Z. Effectively, there's a single temperature that represents the control volume, and you're assuming that all the momentum introduced by buoyancy is used simply to mix this and create a perfectly stirred reactor on top, okay? So what you have is effectively a perfectly mixed hot layer at an homogeneous temperature. You ignore the bottom layer because all you need is the transfer of mass. So for that purpose, you need to be able to calculate the mass. Now, the amount of mass of smoke that is going to go into the smoke layer is defined by the air that is being entrained and by the fuel that is burning and the energy that is being released. Now, the way in which you treat this is you try to estimate the energy that is being released. You take a fraction of it as being lost to radiation, and you estimate empirically what that fraction is. And therefore, that gives you the energy, which can then be translated into a temperature of the smoke that is coming out. And then you create an empirical correlation to relate that heat to an amount of air entrained, okay? So you ignore entirely the production of fuel. You ignore the fluid mechanics that brings air and brings it out, assuming it just simply happens. You ignore all the flow field in the cold area, and effectively all you do is by means of a heat release rate or amount of energy produced, some fraction that is lost due to radiation, and some empirical correlation that relates that heat release rate to the entrainment, you can calculate the smoke, amount of smoke, and the temperature of the smoke that then you input as your only input into the smoke layer, okay? So now, why is that useful? Because as the smoke layer descends and its temperature increases, I can create a criteria that defines the condition for flashover. And that criteria, once you attain flashover, because you know what the velocity of descent is of the smoke layer, allows you to calculate the time to flashover or the TF, okay? So the objective is purely to calculate TF, and therefore, for that purpose, taking this particular approach actually works, okay? Now, there's all sorts of simplifications in there, and we'll go through them one by one, and, but those simplifications, in essence, you need to just simply establish that they are on the conservative side, and that basically enables you, to be confident that your calculation of TF is going to be conservative. So basically, this is what we call a zone model, and it divides the room into two well-defined zones, the upper layer with combustion products and the lower layer, the cold, and implies very strong simplifications, but it allows you to understand the dynamics of the problem. So the velocity is the change in h as a function of time. So basically, you're moving down. The temperature of the upper layer allows you to define a criteria for flashover, and that's what we're going to attempt, to calculate. Now, what are we going to solve? The typical equations. We're going to treat the problem as a control volume. You have the ideal gas law, in this case for the upper layer. Pressure is constant and is ambient. So in this particular case, as I say, you assume that it's an incompressible flow that only brings compressibility through the Boussinesq approximation into the buoyant term. Everything else remains, incompressible. So all the momentum, all the pressure differences are transformed into momentum, basically. So what you have is the ideal gas law expressed in terms of density as opposed to volume. And then you have conservation of mass. So the mass that you input of smoke has to be equal to the change of mass of the control volume. And the change of mass of the control volume is the area of the ceiling times the height gives you the volume, times the density gives you the mass, and the density is a function of the upper layer temperature, okay? So basically, your density function of the upper layer temperature, your height function of temperature. So height times area gives you volume, times density gives you mass. So basically, the mass change in time corresponds to the mass of the smoke that you're inputting. Is that okay? Now, I could create vents, okay, and basically create extraction too, okay? And that just simply complicates the equation a little bit, but it's the same concept. So I'm not going to add it just to keep it simple, okay? Now, your final equation that gives you closure is just conservation of energy, which again is area times height gives you volume times density gives you mass, mCp T, okay? So the change in energy with respect to time is equal to the amount of energy that the smoke is bringing. So it's the mass of smoke times the specific heat times the temperature of the smoke, okay? So this is energy in. There is no energy out because it's adiabatic. And this is the change in energy as a function of time. So effectively, the equations cannot be more simple. They're just simply ideal gas law, conservation of mass, conservation of energy, okay? So that is the way in which you address the pre-flashover compartment. And then you have the post-flashover compartment. And the post-flashover compartment is much more complicated. You know, in that case, you're going to have a lot of things, you know, that you need to address. You have to address the fire dynamics. You know, that fire dynamics is going to produce a net heat flux that goes against the walls that is going to be conducted into the walls. Then at the cold side of the wall, the gradient of temperature is 0, so you assume an adiabatic condition at the cold side of the wall, and the initial temperature of the wall is going to be ambient. So you have an initial condition, an outer wall condition that is conservative, and an inner wall condition that basically gets this heat flux from the fire dynamics, okay? So basically you're aiming at the boundary condition because the post-flashover fire is only important in what pertains the heating of the structure, okay? It has nothing to do with people anymore because people have to be out post-flashover. So all you're dealing with is trying to calculate the net heat flux. And once you have the boundary condition, you can solve a one-dimensional heat transfer equation, you know, that basically allows you to calculate the temperature as a function of the depth and a function of time. So you get Tx of T, okay? And that basically then allows a structural engineer to do a structural analysis. If you give a structural engineer the evolution of the temperature in depth and in time, then they can input that into their own structural models and then calculate how the structure starts deteriorating as it heats up, okay? And you can establish a structural failure criteria, and that will enable you to solve, you know, the problem. And the key for us is to be able to assess, you know, the QNet, okay? And there is, tomorrow I'll go through the framework that does the post-flashover. Today I'm just going to do the pre-flashover. Now, then the net heat flux, if you want to solve the problem completely, you will have to solve energy in, you will have to solve the energy generated, you will have to solve the energy out, which is going to be the integral of the advection term, you know, plus the radiative term of heat losses through the door, the heat going to the structure, and basically the change of energy within the control volume, which is the entire compartment. So basically this is the equation that you need to solve, and this is extraordinarily complex. It's sort of this complex integral differential equation where every single one of these terms is extremely nonlinear. So this is a very, very complicated problem, and again, as I say, tomorrow I'll look into this in its own way, trying to simplify this completely. So let's look how the fire grows in an enclosure, the pre-flashover fire, okay? And how do we address those three equations, the ideal gas law, mass conservation, energy conservation, okay? So let's look at the pre-flashover fire. First thing, heat of combustion, well known, okay? I don't have to worry about that. You stick it in a bomb calorimeter, and effectively you find the heats of combustion. There's not much I can say. The typical thing of heats of combustion for all fire problems is that other than hydrogen, you know, that is pretty high, then you have the non-charring materials who are all between 45 and 50, okay? And then you get all the charring materials, you know, which are 15. So it's pretty straightforward. If the material is charring, effectively you get a heat of combustion of about 15, and if material doesn't char, you get a heat of combustion of about 45 plus. Okay? So there's no great science in there other than just simply getting it out of a test. Okay? Now, spread is a much more interesting problem, and we need to address spread in a simple way. Now, the way in which we address spread is basically we look into the heat release rate, and the heat release rate is going to be the heat of combustion multiplied by the burning rate. So this is kilograms per second of fuel being produced, and the heat of combustion is megajoules per kilogram. So if you multiply this, you get megajoules per second, and that's the heat release rate. So MF is the burning rate, is the rate at which you produce fuel. So the rate at which this solid gets gasified and produces fuel to create the heat release rate. Now, this is the really interesting part about this framework, is the way and the simplicity that they use in splitting the problems in the parts that they are interested in. So if you look at the problem in a slightly different way, you break the burning rate into the burning rate per unit area, kilograms per meter squared per second, okay, multiplied by the area. Now, why do you do that? Because the area is what grows in time. So as the flame spreads and the surface gets more involved, it is going to grow in time, and this term changes much, much faster than this term here. So what you're going to assume that this is a conservative but constant number. So the burning rate becomes conservative but constant. And the reason why we do that is because it changes much slower than the area, because the area is going to increase as the flame spread velocity increases the radius of the circle. Okay? So by recognizing that this change happens much faster than this, you take the error of approximating this with a constant but conservative value, and you focus in the change of area as a function of time. And that's what determines how your heat release rate is going to grow as a function of time. So if you think about this in simple terms, the heat of combustion is a constant, 45 or 15. The burning rate is a constant that I need to estimate, and the area is going to change in time, which is what gives me the evolution of Q as a function of time, the heat release rate as a function of time. So that simple simplification enables us to solve the problem in a way such that we can guarantee that it's conservative and is capturing the feature that is most relevant, which is how the area is increasing. Okay? Now, once again, because you're using this for design, you don't know how the fuel is going to be distributed. You don't know where it's going to be, whether it's going to be homogeneously distributed or whatever, so you take the worst case scenario. What is the worst case scenario? Homogeneously distributed fuel and the ignition in the middle, and it burns as a circle. Okay? It cannot be worse than that. Okay? So in essence, you turn the burning area into a circle, which is pi r squared, and then the radius is the flame spread velocity times time. So then I substitute the radius in here, and I get that the area is pi times the square of the velocity times the square of the time. Okay? Now, at that point, I'm going to make, again, another conservative assumption. I verify that the velocity also doesn't change very rapidly. So effectively, I can assume, again, a conservative velocity to input in here that I can treat as a constant in such a way that everything becomes a constant except for time. So if I substitute the terms, I start here, the area is pi b squared t squared, so I can plug this in here, and then all these terms become constants that I can characterize as material properties. So basically, I'm going to be running tests where I evaluate conservative numbers for all of this and turn all this into a constant that I'm going to be calling alpha. Okay? Now, this immediately creates what we call an alpha T squared fire, which is effectively the heat release rate is proportional to the square of the temperature, of the time. Okay? So it's going to grow in a parabolic way as the square of the time, and alpha is a constant that is a material property that is going to be different depending on which material you're burning. Is that okay? Okay, so it's a very, very simple approach, and that approach, we've standardized it. So people have done a whole bunch of tests, and they've characterized all sorts of different materials, and as a function of that, they've classified the fires in 4 types of fires. A slow-growing fire, where the alpha is going to range between this, and these are parabolic functions of time. The medium fire, and the fast fire, and the ultra-fast fire, and here you get examples of different types of materials, okay, that have been characterized and have been placed within these 4 ranges, that each of them corresponds to a range of alpha. Is that okay? So, lithium-ion batteries, what is the problem? When we design residential buildings, we assume that the type of materials that we have in residential buildings correspond to a medium fire, okay? So all our provisions will be designed in a way such that residential buildings will have a medium growing fire, because most of the materials in residential buildings correspond to a medium growing fire. Now, in parking garages, what do? We characterize the fire in a parking garage as a slow-growing fire. Why? Because the containment of the car doesn't allow for the fire to spread too fast. All the original tests that were done on cars, on vehicles, showed that by the time you ignite the first car, the second car was already fully consumed. So at the most, you can get 2 cars burning simultaneously, and if you want to be super conservative, you might include 3. Okay? Where do you think a lithium-ion battery fire falls in? Basically around here. So the typical alpha for a lithium-ion fire will be about 0.37. Okay, so all of a sudden, the problem from the perspective of life safety of lithium-ion batteries, whether they are in residential spaces or in parking spaces, is that we are not designing these systems to operate with an ultra-fast fire like a lithium-ion battery fire. It's not the energy that they have available, it is the rate at which it gets released. So if I was to treat a lithium-ion battery fire as an alpha T² fire, I would have to place it somewhere around here because it is about double the threshold of the ultra-fast fire. Nevertheless, I am designing everything to be medium in residential and office spaces and everything to be slow in parking garages, including our sprinkler systems. Okay? So in essence, the problem with lithium-ion fires from a real life safety is simply that we are not designing for it. You know, everything that we're putting in place is for a different type of fire, and then all of a sudden we've introduced a hazard that brings to the picture a fire that is completely different to what you are designing for, okay? Which basically reminds you where these design principles came from, because the problem is that today, if you are a practicing engineer in this space, and they say you have to design a residential building, you don't even look at this anymore. You just design the provisions. You design all the provisions that you put in place, and you forget that those provisions were all designed to only work with a medium fire. But this has already even been forgotten. So in the code, you will not find this. What you will find is a reference to the SFP handbook, the Society of Fire Protection Engineers handbook, where you can find this diagram, okay? But it will not be in the code. In the code, it will say, your sprinkler shall look like this, your detection shall look like this, your compartment shall look like this. But they don't tell you why it should look like this. It just tells you that. And then they put a reference at the end of the code saying, for further information, go to here. Nobody looks at the reference, okay? And in essence, then all this basis to the problem gets forgotten. But as you can see, it's a very simple framework that creates a parabolic rate of fire growth that we can assume that is fundamentally conservative. So once I have that, then I can start putting my equations in place. Now, interestingly enough, the first equation is conservation of mass. So the mass of air entrained and the mass of fuel if I add the two of them, gives me the mass of smoke. Okay? So which one is bigger? The mass of fuel or the mass of air? Somebody says fuel, somebody says air. Make up your minds. Which one is bigger? Are the same? Huh? Yeah, this side says air. The other fuel. Okay? Now, this is a really interesting question because it allows a very interesting simplification. So let me show you a little experiment. So this is a saltwater tank. Okay? So basically what we have is a tank of water, and basically is 1 meter by half a meter in depth. So basically the area is going to be 0.5 square meters. Okay? So if I take my ruler and I measure the height, I can have the volume of smoke. Okay? So if I inject a mixture of water and ink that makes this flow a little, well, makes it flow denser than the water, then the flow is going to come down, and it's basically an upside down version of injecting hot gases in cold air. Is that okay? So I can make the ratio of densities coincide in such a way that this saltwater tank can entrain the same amount of air that a hot plume will entrain if you have the density gradient associated to hot gases and cold air. Is that okay? It's just upside down. So you will see the turbulent plume developing, and then eventually, once I inject this, I will get a volume of smoke. Okay? Now, the reality is that I know exactly, because it's a syringe, so I know exactly how much I'm injecting, and as a result, I know what the fuel is, I know what the total is, so total minus fuel gives me air. Is that okay? So let me inject it, and I can show you. So basically, I start injecting it, and you can see the buoyant plume being created, then the stagnation point at the ground, and then the smoke starts moving until it fills the tank. So we will wait until it settles completely, and then you will get the total volume. That is created. You have to wait until it settles a little bit, and then you look at your ruler, and you can measure the volume. So, once it settles down, I can measure it, and basically the amount of fuel, which is the injection, is 10 cubic centimeters. The tank is 100 times 50, and the height of the smoke layer is 5 centimeters. So effectively, the mass of fuel divided by the mass of air is 10 to the minus 4. So you have 10,000 times more air than you have fuel. What does that mean? Can you neglect the fuel? So basically, this is your equation. The mass of smoke is equal to the mass of fuel times the mass of air, but the mass of air is 10,000 times bigger than the mass of fuel. So as a result, I can neglect this, and I can just simply approximate it and eliminate the fuel. I can ignore it, and basically, the amount of air entrained is equal to the amount of smoke. Are we happy with that? Fully demonstrated by a beautiful and simple experiment. Okay? So, obviously there's some imprecisions in there because I've not played with the density and so forth, but in essence, when you're talking about 10,000 times, whatever imprecision we put in there is negligible, okay? But that gives you a sense of a simplification I can make. So now, if I do conservation of energy, it simplifies itself completely because the heat release rate now is I only have to include the mass of air times the specific heat times the change of temperature, and I can solve for the temperature of the smoke. Okay? Very simple algebra. I divide by this, Q divided by this gives me a characteristic temperature, plus the ambient temperature gives me the temperature of the smoke. Okay, so now I have the temperature of the smoke. Okay? So then I need to get the mass of air entrained. Now, what I'm going to do is a series of experiments to create a simple correlation, okay? So I have identified that the hotter the fire is, the more heat release rate, the more air entrained I get, and the higher the area of entrainment. In other words, the clean space through which the air come in, the height, is going to also increase the entrainment. As I shrink the height, I'm going to get less and less and less entrainment because I'm reducing the area through which I can get the entrainment. So the variables I'm going to be playing with is the heat release rate, and I'm going to, in a hood, I'm going to allow the smoke layer to descend in such a way that effectively I'm extracting the same amount of air that I am putting in so that I get a steady state position of the smoke layer and therefore a steady value of the height, okay? If I reduce the velocity of the fan, I decrease this value and the smoke layer descends, okay? If I want to bring it up, I increase the fan value and the smoke layer ascends, okay? So I can construct a very simple correlation that takes into account two variables, the heat release rate and the height. So what I'm going to do? I'm going to be measuring the amount of air entrained as a function of the height and as a function of the heat release rate, okay? So in essence, I have on the x-axis the height, in the y-axis the mass of air entrained, and the different data sets correspond to different heat release rates. As you can see, as you increase the heat release rate and it gets bigger, you get more air entrained, and as you increase the height, you get more air entrained, okay? Now, this is where you use your brain. So then you go to Navier-Stokes, you do a very simple scaling analysis, you take the buoyant term, which is the driving force, and you find out that effectively the scaling criteria is the heat release rate to the 1/3 and the height to the 5/3. And that actually just comes from doing scaling analysis of Navier-Stokes with a buoyant term, okay? So basically, this is a scaling analysis, and it comes in with all these constants: gravity, the density of the air squared, specific heat, and the ambient temperature. These are all the constants that are issued from the scaling analysis that correspond to the conversion of heat release rate into density, basically. Okay? So the heat release rate turns into temperature, and the temperature into density, and you put that on the buoyant term of Navier-Stokes, and that gives you this scaling coefficients. Okay? So the exponents of 1/3 and 5/3. Okay? So in essence, this is what comes from scaling Navier-Stokes. And what is the empirical correlation? I make all the data collapse to find the value of E. Okay? So in essence, I am going to, instead of putting H and Q here and mass of air entrainment, I'm going to put mass of air entrainment here, and in here, I'm going to put Q to the 1/3, H to the 5/3. And what that does, it collapses all the data into a straight line. Okay? And the slope of the straight line becomes E, and that's the empirical correlation. Okay? So now I have my mass of air entrainment as a function of the heat release rate and the height of the smoke layer. Okay? So everything is a constant, and by collapsing all the data, I find the entrainment coefficient of 0.2 for a circular pan, that is completely unobstructed. So people have been doing these tests for different configurations: a corner fire, a line fire, different geometries will give slightly different constants. It will not alter the scaling rules, so it will still be Q to the 1/3, H to the 5/3, but it will change the entrainment correlation. So what have I done? I have circumvented all the fluid mechanics by a simple empirical correlation. So this is complex fluid mechanics because it's buoyant entrainment that brings three-dimensional airflows, with all these shedding vortices and all these different things. I've ignored everything and turned it into a very simple empirical correlation. Is that okay? Now, the more I obstruct, the lower this coefficient is, so the conservative case is to use the 0.2, because that will be the worst case scenario, the one that produces the most smoke. Okay? So now that I have MA, I have the mass of smoke, and I have the temperature of the smoke, and what I'm going to be doing is now solving the control volume of the upper layer. So the control volume of the upper layer, the mass of the control volume is going to be the density times the area of the ceiling times the height, gives me the volume. So I get volume times density, the mass of the control volume, and I do conservation of mass. And the input is the amount of air that comes in, which is the same as the smoke. Okay? And basically, this is my equation for conservation of mass. Conservation of energy is going to be the same, but this time is M, the mass of the control volume, times Cp, times the temperature of the hot layer. Change in time is the input, which is the amount of heat that is being brought in, the enthalpy that is being brought in by the smoke that is coming in from the bottom. Okay? So now I have all my equations, and I can put them very nicely in a list. Ideal gas law, heat release rate is alpha T squared, okay, where alpha is defined by what is the occupancy on the type of fuels that I expect in the room. I can go to conservation of energy at the smoke, which gives me a temperature of the smoke. I get the mass of air entrained from the empirical correlation. And as you can see, it depends on H. So I have to solve simultaneously the conservation of mass and conservation of energy because they all depend on H. So effectively, I can find, discretize the value of the increment of H for every time step, and I can discretize the increment of temperature for every time step. This I can solve in a spreadsheet. Oops. So here's an example where I put typical dimensions of a very small room, and I can put these equations all into a spreadsheet and literally solve the problem as a function of time. And what you get is that your smoke layer starts at the ceiling, 2.75 meters, and as time progresses, it descends until eventually it hits the floor, and your temperature is ambient, and eventually it accelerates and when you reach flashover. So normally we use a threshold of 600 to determine flashover, and again, that's an empirical threshold that we put in place. So here you will get flashover in about 90 seconds. Now, as you can tell from the experiment that I showed you, this is conservative, 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 conservative. Okay? So in essence, I ended up with a time to flashover of 90 seconds, when in reality, if you look at the test that I showed you, the time to flashover was about 4 minutes. Okay? But you can see the conservatism I've embedded at every level, of the problem. That was not a circular fire going radially. It was obstructed on the one side, so your entrainment coefficient was not 0.2, and it was not adiabatic. You were losing smoke, through the door. So there's all sorts of different components that are exceptionally conservative, but that nevertheless, allows me to make a calculation that gives me the value that I'm looking for. So, in essence, this is the concept that you're working with. So it's a concept that is very straightforward. It uses a methodology that is very straightforward. And if you have the time, I will suggest the exercise of just discretizing the equations and putting them in place, because in a way it shows you very clearly how you can construct a very, very simple story that gives you all the answers that you want. Okay? Now, if I wanted to know, for example, obscuration, I can put a soot volume fraction. All I have to do is create another conservation of mass where I'm going to have a soot yield that is basically proportional to the heat release rate. Okay? So a fraction of the heat release rate is going to be converted into soot, and that I just simply do conservation of mass, add another equation, and boom, now I know also what is the concentration of smoke in the smoke layer. Okay? So you can add bells and whistles to this, and but you don't have to, because somebody obviously has already done it. And so if you go to the website of NIST, you will find a zone model called CFAST, and basically it's a very sophisticated zone model that not only resolves the whole compartment, it has the whole array of different correlations that you can use for the air entrainment, and you can pick and choose the one that is more appropriate. Not only does that, it also includes multiple compartments, so you can actually move smoke from one compartment to another, so you can actually release smoke to make this calculation less conservative and put it into the next compartment and the next compartment and the next compartment. And it includes mechanical ventilation, all sorts of things. So they create a network model, but basically on the principle of just these simple controlled volumes and no fluid mechanics at all. The fluid mechanics is always substituted by very simple empirical correlations. Okay? So in essence, what is the computationally intensive components have all been eliminated, and you end up with an extraordinary simple model. So if you run CFast on a 5-room configuration with every bells and whistle, you can run a scenario, I think, in about 4 or 5 seconds. Okay, so you input the thing, you hit enter, and then the answer is spit out. Okay, so there's no computational weight into this, so it allows you to do a very extensive parametric study. So you can actually test all your uncertainties. And what happens if the fuel is not A, but it's B? What happens, if I increase the ceiling height? What happens if the window breaks? You can test all these things very rapidly and do a whole array that basically allows you to gain confidence on all the uncertainties that could potentially be there without the weight of the computational cost. Now, once you narrow everything down, if you want to refine it, then maybe you want to run a CFD. Okay, but there is no point in running a CFD that is so complex until you have done a clear suite of these zone models to give you a sense of where you are. And then if you want to refine, as I say, you can do something a bit more sophisticated. So the zone model divides the room into 2 well-defined zones, the upper layer and the lower layer. Provides the evolution of the height and temperature of the hot layer. It depends on an entrainment correlation, and you have to use the appropriate one. Results from a simple mass and energy balance between 2 control volumes, and breaks down when the smoke layer gets too close to the floor, because the entrainment correlation is not valid anymore. So when the smoke layer has descended too far, then there is really no entrainment correlation that does that for you. So when you look at the data here, at some point you need to truncate it, because otherwise the temperature goes to infinity. Okay? When there's no more air entrainment, then effectively the mass becomes 0, and it is a discontinuity. So in essence, there are some limitations, but if you understand how the model gets constructed, then those limitations are pretty straightforward to handle. So that gives you a little bit of a sense of a practical application of great simplicity. But that practical application relies on a number of assumptions. So for example, I made the assumption that the flame spread velocity was a constant. I made the assumption that the burning rate was a constant, and I blended them into this alpha parameter that became a very sort of coarse empirical correlation. Now, the reality is that the flame spread velocity is not a constant, okay? And the burning rate is not a constant, and all these things are a lot more refined. So what we will do tomorrow is I will start with that alpha t squared expression and look into the different ways in which we can assess these flammability parameters, and what kind of tests and what kind of analysis we can put in place to actually establish with a lot more precision what my flame spread rates are going to be, what my burning rate is going to be. So then you don't have to use this coarse alpha value, but you can dig deeper and find something that is more adequate given whatever specific problem you're working with. So today I've done the first layer of simplicity, and then tomorrow I'll get a little bit deeper on the flammability parameters, and then I'll do the post-flashover framework, again in its simplest version, with no need to get too much deeper than that. So with that, I'll close the whole thing. But if there's anything, is there anything in particular that you think I should be covering that I haven't covered so far, so that maybe tonight I can prepare something, in addition? Is there anything that you wish I would have touched upon?
Well, battery fires are my interest, but you have talked about them. So, you have given some data on it.
Yeah, and I think the one part that I will not want to get into when it comes to battery fires, because I mean people are familiar with the literature, is how they fail. I think for me, what is really important is we assume that they will fail. I want to design a building that actually can cope with that failure. Okay, and that's kind of what I've been trying to explain. Okay, the complexity of the failure mode, is very high and very uncertain. So in a way, right now, we are obliged to change the way in which we design buildings to be able to cope with those fires under the assumption that they are going to happen. Okay, so in essence, if you allow me not to get deeper into that, I rather not. Yes. Yeah, so I'll try to put something together, and there are certain aspects of fire dynamics that are still very, very open. I mean, one of them is the development of CFD tools. The other ones are sort of the extreme forms of fire dynamics, like smoldering, for example. So I try to put some of that in there, and I'll try to make sure that I get there and try to explain, a little bit of that.
Could you say again the name of the NIST code?
C, fast.
C, fast.
Yeah, fast like fast, but with a C in front. C, fast. Okay? Okay, so I think it's 5:20, and I was told that there's a dinner today, and I have to finish by 5:15. So thank you so much for your attention, and then we'll pick it up tomorrow. Thanks.